today's topic is spinodal decomposition. So I'm sure that you might get a question from this in end semester, most probably. So you might get a question like this, like what is the difference between precipitation and spinodal decomposition? Right? You have to differentiate them. You have to write the points. How precipitation is different from spinodal decomposition. Precipitation, everybody knows, right? We have one matrix and one second phase particle. That is precipitation. The best example, if you remember, alpha will give you a simple example. And this kind of precipitation is seen in this kind of alloy system. From the last line. Alpha supersaturated solid solution decomposing in this kind of system, alloy system. Anybody from girls? I want to from girls. Aluminium copper. Aluminium only aluminium. Aluminium copper system, very good. So which one is the matrix? Let them speak. Which one is matrix? Theta is the matrix. Theta is the precipitate. Alpha is the matrix. Fine. The matrix. And this is precipitate. Then you can see the difference between alpha and theta is what? There is a difference in what? Exactly. What is the difference between this alpha and theta? Pure, you cannot say pure, it still contains copper. Difference in crystal structure. Alpha is what? FCC. Theta is orthorhombic. Right? And you start with this one. This one will be what? Which crystal structure? Alpha super saturated solid solution is. This is also FCC. You end up with FCC plus orthorhombic. So what I want to say is, if precipitation is happening, you will get one matrix and one precipitate. And matrix and precipitate have different crystal structure. But if you look into spinodal decomposition, the situation is something different. Now I would like to discuss that. Spinodal decomposition. You can see, I can simply write spinodal decomposition is like this. Alpha will become alpha 1 plus alpha 2. So this is spinodal decomposition. Can you tell me what is alpha and what is alpha 1, alpha 2? It is a single phase. Alpha is a single phase. Yes or no? It is a solid solution. Everything is in solution, right? It is a single phase. Everything is solution, it is a single phase. This is also a single phase, but this is supersaturated. Okay? But this is single phase. Now it is giving you two different phases, alpha 1 and alpha 2. Right? So a single phase will decompose into two different phases. But interesting point is this is alpha, but this is also alpha 1. This is alpha 2. This is not beta, this is not gamma. Or this is not theta or something else. Okay? So it means this is also a single phase. Same. Suppose this is FCC. This is also FCC. This is also FCC. Right? It means single phase is decomposing into two different phases but having same crystal structure. But look at the precipitation. Matrix is different, but precipitate is different crystal structure, right? But here in this case, all are having same crystal structure. What is the difference then? Just tell me. Suppose B. A is one element, B is another element. What may be the difference? Just imagine composition difference, maybe. So alpha 1 and alpha 2 are different in composition. Okay. You are getting my point? This particular single phase is made up of two elements, A plus B. let it be like zinc, aluminium and zinc, for example. Let it be aluminium and zinc. So suppose this is aluminium and this is zinc. So alpha 1 will be a phase which is rich in aluminium, right? So what will be the alpha 2? Very good. It is a phase which is rich in zinc. Because we have two boundaries. The one boundary is pure aluminium, and the boundary is pure zinc. If you change the composition, you are increasing aluminium and decreasing zinc. But if you move in the reverse direction, you are increasing zinc, decreasing aluminium. You know the phase diagram already from physical metals, right? This is the situation. This is aluminium ring, this is zinc, right? If you can write X what should I write? X?
Zinc.
And this is temperature. Temperature versus composition. Phase diagram. Right? So that means this is aluminium rich phase, this is zinc rich phase. But they all have same crystal structure, but difference is the composition. And you have to remember one important line here. If composition will change, then lattice parameters also changes. You measure the lattice parameter of copper, for example, but you are adding zinc into it. The lattice parameter will not remain same basically. It will change, right? The lattice parameter of this one will be different from this one and will be different from this one. That is happening due to change in composition, that's all. So you understood one, this is one of the best difference. And you also can write one important line. In precipitation, nucleation happens. But in spinodal decomposition, there will be no nucleation. It is a spontaneous process. It is a spontaneous process, you can write. Precipitation involves nucleation. Whenever there is a phase transition or phase transformation, right? What happens? A nuclei always forms. From a parent phase, a product nuclei forms, then it will grow. Right? You know people. Nucleation, then growth. Right? Thus, that kind of things happens in the precipitation process. But in case of spinodal decomposition, automatically alpha will decompose into alpha 1 and alpha 2. Automatically. That is spontaneous process. So, spinodal decomposition does not involve what? Precipitation. Nucleation. You have to remember. So, this is another difference. I think you could have understood this one. Next one is I can write. You can write one important line now. Spinodal decomposition is seen in that phase diagram. Spinodal decomposition is seen in that phase diagram. In which there will be a miscibility gap. In which there is a miscibility gap. You understood miscibility gap. Miscibility gap means, suppose you are adding aluminium into zinc and you are adding zinc into aluminium. Sometimes they will separate into two different phases, right? That means 100% zinc cannot be soluble in aluminium or 100% aluminium cannot be soluble in zinc. You understood my point? So the phase diagram which shows miscibility gap, those kind of phase diagram will show you spinodal decomposition only. If there will be no miscibility gap in the phase diagram, there will be no spinodal decomposition. Miscibility gap, you understand my point? Suppose you are adding 1% zinc into aluminium. Zinc is soluble in aluminium, that's fine. That is the solubility limit. Second, you are adding 2%, 3% like this. If you increase more amount of zinc into aluminium, a time will come, they will separate. Zinc will not become soluble. So there is a miscibility gap. Miscibility and gap, right? Okay. So spinodal decomposition always seen in those phase diagram, we show miscibility gap, right? Now I would like to draw a miscibility gap phase diagram. So what should I do first? This is a simplified phase diagram. Phase diagram means what should I write in this y-axis? Phase diagram. Temperature in degree centigrade, very good. And in this direction, what should I write? Composition, very good. Composition is x. Temperature versus composition. Phase diagram. I want to show you miscibility gap. So here I am taking an example. Okay, this is A, this is B. Now, this is very interesting. Anybody remember which kind of phase diagram is this? Isomorphous phase diagram, right? Copper nickel system, if you remember. But isomorphous system means every time you add copper into nickel or nickel into copper, both are soluble completely, right? So this is isotope phase diagram, but miscibility gap is this one. This is your miscibility gap. This part. You might get a question that draw a phase diagram showing miscibility gap. This is a phase diagram, right? So what should I write? Can you tell me quickly? So here what should I write?
Liquid.
What is this?
Liquid.
What is this zone?
Liquid.
Liquid, very good. What is this zone?
Liquid plus
Liquid
alpha.
plus
Alpha.
alpha, very good. And what is this zone?
Alpha.
Alpha, very good. Now what is this? You have seen the spinodal decomposition already. Right? Alpha, very good. You understood now? You can see this single phase is now not stable. It dissociates into alpha 1 and alpha 2. But there is a temperature, that means you understood there is a temperature limit. So this is the temperature limit. If you go below, you take single phase alpha, you go below this temperature, they will automatically separate into alpha 1 and alpha 2. But if you are in this region, alpha will remain. Okay? So alpha 1, alpha 2 all have same crystal structure. The difference is what? Alpha 1 and alpha 2 are different in composition of it. One will be A rich phase, one will be B rich phase. Okay, fine. What should I write here? What should I write here?
Alpha.
Alpha, only alpha. No? This is
Alpha.
This is alpha. But that is the reason why you are showing miscibility gap. And you understood the temperature also. So below this temperature, miscibility gap is happening. And this region is also single phase. But this region is two phase, alpha 1 and alpha. Okay, to explain this one, I draw two diagrams. So first diagram is like this. And a diagram is U. So this is G versus X. This is also G versus X. So diagram is like this. Now I have a question. Tell me, in between these two diagrams, G versus X, G means free energy versus composition diagram, right? In between these two diagrams, which one is showing stable alpha and which one is saying unstable alpha? Just wait. If you know the answer, you just raise the hand. You understand the point? This is G, this is X. This is also G. Okay. And this is what I know, this is alpha phase. This is also alpha phase. But tell me which diagram is showing stable alpha, which diagram is showing unstable alpha or unstable alpha. This is very simple. No, don't answer. No. Let me see how many of you can answer. 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. Question is very simple. Again I am repeating. These are two free energy versus composition diagram, right? Which one is showing stable alpha, which one is showing unstable alpha? Okay, fine. First one is stable or unstable? Unstable.
First one is stable.
You have studied thermodynamics, now you are studying phase transformation since 25 number classes. The first one is showing stable. This is A end, this is B end. Yes or no? Fine. This is A end and this is B end. Right? Free energy. See, you see, suppose you start with this point. Fine. You are adding B into A. What is happening? The free energy decreasing or increasing? Decreasing. This is free energy decreasing, right? You are adding B into A, free energy is decreasing and reaching at this point. Right? Similarly, you add A into B. What is happening? Free energy starts from here. And you are adding A into B. So what is happening? Free energy decreasing or increasing? It is decreasing and reaching at this point. Free energy is decreasing. You are adding B into A or A into B. Free energy is decreasing. And both are forming a single phase, that is alpha. So it is stable phase diagram. Stable alpha. So second one is stable or unstable? Unstable obviously, because you can see free energy is increasing. You are adding B into A or A into B, free energy is increasing. So it is unstable. So that means That means second kind of phase diagram will show you, sorry, free energy versus composition diagram is showing alpha will decompose into alpha 1 plus alpha 2. You understand that point? As I told, spinodal decomposition means alpha will decompose into alpha 1 plus alpha 2. So which situation is favorable? First one or second one? Second one, because that is unstable. That's why alpha split into alpha 1 plus alpha 2. That means by converting alpha 1 to alpha 1 plus alpha 2, the free energy is reduced. System always try to reduce its free energy. So if alpha will be there, its free energy is higher. But if it becomes alpha 1 plus alpha 2, its free energy will be reduced. So that is the thing what is happening in spinodal decomposition. Okay? Can anybody justify? Okay, let me justify it. Okay, can you tell me, suppose I am taking a temperature of this one. I am taking the composition of this one, and also I am taking the composition of this one. That means I am choosing an alloy of this particular composition and this particular composition. Now you will tell me in the first case what is the free energy of alpha. This is the point. This point shows the free energy of alpha, G alpha element. Free energy of single phase alpha. Now suppose this kind of alpha want to split into alpha 1 plus alpha 2, right? I told alpha 1 alpha 2, what is the difference? Tell me.
Microstructure.
Composition difference, right? There will be difference in composition. Someone will be A rich, someone will be B rich. If someone will be A rich, I can choose this point for example. I can choose the point of this. This is A rich, and I can choose the point here. This is B rich. Okay? And what is the free energy of the mixture? Tell me, what is the free energy? This is alpha 1, and this is alpha 2, and this is alpha, for example. Anyway. What is the free energy of alpha 1 plus alpha 2? Straight line. This is the free energy of the mixture alpha 1 and alpha 2. And at this composition, this is the point. Right? So free energy of alpha is this one, and free energy of alpha 1 and alpha 2 mixture is this one. So which one is higher? Free energy of alpha is higher or free energy of alpha 1 plus alpha 2 is higher?
Free energy of
Alpha 1 plus alpha 2 mixture is higher. So can this one decompose into this? Is it possible?
Yes.
Is it possible?
Oh.
Alpha become alpha 1 plus alpha 2. No, why? Because you have to increase the free energy. If you want to increase the free energy, the reaction will never be feasible. If the reaction wants to be feasible, free energy must be decreased, or free energy should be negative. Okay, you understood up to this, or you have any confusion? Right? So this point is showing you free energy of the mixture of alpha 1 and alpha 2. This point is showing you free energy of alpha only, single phase. This is G alpha 1 plus G alpha 2. This point. And this point is G alpha. Okay? But now this one, again, this is the composition. So this point shows what? This point will show G alpha, varying free energy of the alpha. And this one, suppose I am choosing now one A rich phase, one B rich phase. This is A rich phase, and this is B rich phase. And I want to find out so this is alpha 1, this is alpha 2, and I want to find out the free energy. So what I can do, I have to join, and at this composition, this is the free energy of the mixture. So this is free energy of the pure alpha, and this is the free energy of the mixture. So now tell me, alpha will split into alpha 1 and alpha 2, is it possible? Yes, because the free energy of the mixture is lower. Right? So this free energy, that means this alpha will split into alpha 1 plus alpha 2 easily. And you can correlate this one with, check the diagram. This is phase diagram, this is free energy versus composition diagram. You understood the part? Up to this? Same way now, this one and this one. This is this kind of thing. So this is splitting into alpha 1 plus alpha 2, like this. But can you tell me, this kind of splitting will proceed further, or it will stop? This is the first. this will continue or it will stop. This is split into this two. Then it will continue or stop. Continue or stop. You can just think of it. Continue, very good, because you can reduce the free energy further, right? So again you change the composition. You take this one and this one. You join it. Again this will split into this. Further it will continue. Further it will continue and finally it will reach to the last point. Suppose you join these two, it will reach to these 2 points because this is the minimum free energy possible. So every time this alpha 1 and alpha 2 will split to new composition, one will be A rich phase, one will be B rich phase, but they have same crystal structure as alpha. So second case shows splitting, but first case is not showing splitting because first case alpha is already stable, but second case alpha is unstable. So it's split into alpha 1 and alpha 2. I think up to this it is clear. If you go through the textbook, you cannot understand, I am sure. So that is why you should attend the classes. It is not easy.
Sir, finally हम लोगों को लास्ट वाला एक पोजीशन मिलेगा जिसमें कम फ्री एनर्जी है. बीच वाला तो फिर ऐसे बढ़ना फिर अनस्टेबल हो जाना फिर बढ़ना फिर अनस्टेबल हो जाना.
This reaction will continue. Actually, you understood that means this will finally decompose into this. That is the end.
मतलब जहाँ पर वो ग्राफ में से अल्फा जहाँ पर इसको कट कर रहा होगा उसके नीचे तो अल्फा स्टेबल हो रहा होगा और यहाँ पर अल्फा कम हो रहा होगा.
I think up to this it is clear. You should write some points. Please. Don't go into the depth without being clear. This is composition axis. This is temperature axis. This is alpha. This is alpha also. This is alpha. This is alpha plus alpha 1 plus alpha 2. This is liquid. This is liquid plus alpha. So you have to remember this point and this point are called binodal point. Right? Binodal. This point and this point are binodal. And this point and this point are called spinodal. Inside 2 points are spinodal and outside 2 points are called binodal. And binodal spinodal will meet at a single point. This is the point. Both are meeting at a single point at this temperature. I can write
3.5 number.
सर आप एक बार क्लास बोले थे वो स्टीम को हम लोग उसका ट्रांजिशन टेम्परेचर है ना 727 उसके नीचे हम लोग हीट कर रहे थे तो उसमें क्या हो रहा था वो जो सीमेंटाइट है वो स्फेरिकल शेप हो जाता है तो वही स्पिनडल दिखा
नहीं, that is precipitation. Carbides form हो रहा है. यहाँ पे तो solid solution form हो रहा है. Alpha 1 and alpha 2 are solid solution. A is in B, B is in A. But one is A rich phase, one is B rich phase. Everything is solution means it is a solid solution. Precipitate means different thing, no? That is carbides, nitrites, carbon nitrates.
लेकिन उसमें स्फेरिकल फॉर्म में हम लोग प्रेसिपिटेट
हाँ, वो precipitation. That is precipitation. Gamma will decompose into alpha plus F3. That is precipitation.
वो रूम टेम्परेचर भी सीधा उसको हम लोग फिर टेम्परेचर तक हीट किए लेकिन बिलो 727 तो उसमें क्या हुआ कि सीमेंटाइट आपका स्फेरिकल बना तो इसलिए
That is changing morphology of the precipitate. You can make the precipitate spherical. If initially it is not spherical, you can make it spherical. And you know why spherical precipitates are important, right? Because the distribution of stress will be uniform. There will be no crack initiation sites. But that is precipitation. That's why I told initially difference between precipitation and see gamma decomposes into alpha plus Fe3C. Right? Alpha is what? DCC and Fe3C is orthorhombic. Different crystal structure completely. Right? One is matrix, one is precipitate. But here in alpha decomposes into alpha 1 plus alpha 2. Here same crystal structure. Alpha is having crystal structure of alpha 1, alpha 2, all the same. So suppose it is FCC. Fine. Only there is a change in composition. And all are solid solutions. If you measure the strength, for example, suppose the reaction is happening, it gives you alpha gives you alpha plus theta, and the reaction gives you alpha 1 plus alpha 2. So in which case you will get more strengthening. First one, this is one, and this is. So in which case you will get more strengthening. First or second? First one, because that is precipitation strengthening. Precipitation strengthening is a very high level of strengthening. You will get very high strength. But second one is a solid solution. It will give you strength, but it is not so high. Right? That's why some people also don't require spinodal decomposition because it will not give you more strength. But if you can get precipitate, that will give you very high strength. You people can check today's photos I have sent you. Phase transformation page. You can see two different colors, microstructure. One is alpha 1 and one is alpha 2. If somebody will ask, give an example, you can give an example of aluminum zinc system. Aluminum zinc system is an example of spinodal decomposition. One will be what? Aluminum rich phase and there will be zinc rich phase, right? Second example is aluminum zinc copper. You can write if you want. Aluminum, zinc, copper. What is the difference? Three elements are present, right? So one will be copper rich aluminum zinc phase, one will be copper deficient aluminum zinc phase. If you want, you can write.
सर ये एल्यूमिनियम जिंक कॉपर वाला में AI तो स्ट्रिंग नहीं बन जाएगा, प्रेसिपिटेट भी तो बन सकता है.
AlCu will form only if you get particular ratio. It is a compound. Compound always forms when they are in certain proportion, like H2O. H2O will never form if you take 10 number of hydrogen, 1 number of oxygen. It will never form. You have to take 2 atoms of hydrogen, 1 atom of oxygen, H2O will form, right? Like Fe3C. You take suppose 100 number of iron atom, 1 number of carbon. It will never form Fe3C. Unless until you have 3 number of atom of iron and 1 number atom of carbon, then Fe3C will form. That is the rule, no? Compound, how compound form? If they are in a ratio, a particular proportion, right? If copper amount is not exact, and with aluminum we have also zinc. So interaction will be there. That's why we have a parameter omega. When we are talking about solutions, we are talking about omega always. You remember omega? Anybody remember omega? What is omega?
Omega which is number of
You have given mid semester, you don't know what is omega.
number of
What is this omega? Tell me. This is called interaction parameter. See, if you have pure aluminium, there is no interaction at all. All are friends. Now all are aluminium atoms. All are very good friends, like family. Right? But if you add copper is different thing. So they will start interacting. They may become good friends, or they may fight. Right? Aluminium don't want copper. I don't want you. Right? You go away. Right? So that is interaction parameter omega. Omega is applicable in which kind of solution? Ideal or non-ideal solution? Or ideal solution or real solution? Tell me. Omega will be used in ideal solution case or real solution? Thermodynamics पढ़ लिए अब ये बताओ. Real solutions, very good. Because ideal solution delta S mix is equal to 0. ये ओमेगा कॉन्सेप्ट कहां से आ रहा है? ओमेगा कॉन्सेप्ट ये फॉर्मूला था ना, याद है कुछ? डेल्टा H is equal to omega XA XB. XA is mole fraction of A, XB is mole fraction of B, and omega is the interaction parameter. This is applicable for real solution. Fine. But if you are talking about ideal solution, delta S mix is equal to 0. This is for ideal solution case. So there will be no omega because delta S mix is 0, right? Why this is 0? Because omega is 0. Why delta S mix is 0? Actually omega is 0. That's why.
Bond energy of AP is equal to the bond energy.
You know, yeah, you remember the bond concept. Bond energy and bond strength. If you are getting still confused, you remember. Suppose I have a single phase alpha. So free energy of alpha will be what? Can you write for a real solution? G alpha. Please write it. I want you to write it. What is the expression of G alpha? Alpha is a single phase, and what is the free energy of single phase alpha?
Epsilon x3.
Then? Yes or no? You recall this one?
One of the example
This is free energy of the mechanical mixture and the free energy of mixing.
mixing.
Right? What I can write further? This is free energy of pure component A into fraction of A. This is free energy of pure component B into fraction of B, and this is due to mixing. And further what I can write? Xa plus V naught B XB plus delta G mix means delta H mix plus minus.
T delta x mix.
Right? This is the expression. Delta G mix means delta S mix minus T delta S mix. Okay. Instead of delta S mix, what I can write? Can anyone tell me? Instead of delta S mix, delta S configuration. This delta S mix is nothing but a configurational entropy. You have to remember. Don't mug it up. Just understand the concepts. This delta S mix means there is a configuration. You are adding two elements. Two elements can arrange in any form, anywhere they want to arrange. Probability. Right. So more is the arrangement, more will be the delta S mix. That is delta S configuration. Instead of delta S mix, you can write delta S configuration. Omega, what is the formula? What is the formula of delta S configuration? K, L and W. K, L and W. K is what? Boltzmann constant. Logarithm Ln, then W means number of microstates for a given microstate. Okay, fine. If you further derive it, at the end what you will reach?
Binary system will be minus R XL
Minus RT or sorry, RT only RT XA ln XA plus XB ln XA. You can write like this. V naught A XA V naught B XB plus if delta S mix is for ideal solution is 0, but if it is not an ideal solution, real solution, what I can write omega XA XB, right? You understand no? For this one, and for my this one it will be plus RT. Okay, I am writing here plus RT XA ln XA plus okay, fine. Sorry. This is the expression, final expression. G naught XA plus V naught B XB plus omega XA XB plus RT XA ln XA plus XB ln XB. For binary system, if you have n number of system, you know what to do. Summation of I if you want to n. You can write. Suppose you have only pure A. You don't have any kind of B. So what will happen to delta S configuration? 0 हो जाएगा. Very good. Excellent. If you are dealing with a pure element, for example, then delta S mixing or delta S configuration will be 0. Okay? But the moment you are adding 2 elements, 3 elements, 4 elements, delta S configuration will increase. Like that. क्योंकि मैं पता है क्योंकि इसको अगर मैं क्या किया 1 तब पूरा 0 हो जाएगा नहीं. एक तरफ 0 हो जाएगा ना, सपोज xb is 1, xi will be 0 obviously, because xi plus xb is equal to 1 होना चाहिए ना, fraction should be equal to 1, right? एक को अगर 1 करूंगा दूसरा 0 हो जाएगा, तो फिर पूरा टोटल 0 हो जाएगा. You understood the point? Huh? Okay, anyways, so what I am to say is, up to this, so that means delta H max can be 0, delta H max can be, sorry, right? Next can be, these are the three situations. If omega is 0, delta S max is 0. If omega is positive, delta S max is positive. If omega is negative, delta S max is negative. Simply. Up to this it is fine now. So basically, for an isomorphous system, if we are talking about isomorphous system, what is happening? A is neither reacting with B or B is neither reacting with A. Both are fine, both are neutral. So that means delta S max is 0 for an isomorphous system. It is okay. But if you are talking about delta S max is positive, what it means? It means A don't like B or B don't like A. They will get separate out from one another. One will be A rich phase, one will be B rich phase. Kind of. You understood? Again I am saying delta H max is 0 means omega is also 0. That's why delta H max is 0. If this is the situation, that means A is neither reacting with B or B is neither reacting with A, but both are neutral to one another. That is an example of isomorphous system, right? But second case, delta H max is positive. Positive means they don't like one another, they repel. A will repel B, B will repel A. Right? That is the situation. Okay? But if delta H mix is negative, then they both like each other, right? So A will react with B or B will react with A at a particular composition, and they can form a strong compound. Because they are liking each other, they will form a strong compound. You cannot easily break. And if a compound is very strong, its melting point will be high or less? High. You cannot break the bonds easily. You understood the point? So for this one, this situation will give you a strong compound formation. Right? And this situation will give you separation. Phase separation or segregation. Right? Because they don't like each other. And this situation is neutral. First one is neutral. They will fight with one another, but they will not react, not repel. These are the three important points to remember. Now tell me, for miscibility gap, which one is important out of these three? Or second one?
Line.
Second one, very good. So you have to remember, if somebody will ask for miscibility gap, delta S needs to be what? For miscibility gap, delta S needs to be positive. That's why one phase is A rich, one phase is B rich. Okay, so this is, so what I can write, omega is positive. That means, that simply means delta H means delta H is positive, and delta H means is greater than, you have to write. This is the situation for miscibility gap. Omega positive होगा तो delta H mix positive होगा, obviously because delta H mix is omega x x t. Fine. And if delta H mix is positive and delta H mix is greater than T delta X, then it will be what? It will give you miscibility gap. This is the situation for miscibility gap. Okay, now try to draw a free energy versus composition diagram for miscibility gap, please. Try. This is alpha. This is alpha 1 plus alpha 2. This is temperature versus composition. So this is given. Temperature versus composition is given. What exactly it is saying? It is saying alpha become. Now I want to draw, or you people want to draw free energy versus composition. G versus X square. G versus X. Like in mid semester you got a question now. Draw isomorphous phase diagram and draw G versus X curve. And you people have drawn it well. Suppose you take a temperature. Suppose obviously you should ask me what is the temperature, right? Suppose I want the temperature of this. Khali alpha right now this one. Right? Suppose I am choosing a temperature of this one. Let me take the temperature of this.
Alpha right?
Or you take room temperature. Bottom one. One hint I can give you, just check the example of when alpha is unstable. That will help you. I have drawn two alpha. One alpha is stable alpha, one alpha is unstable. That will be used. And next hint I can give you, left side alpha is stable phase, right side also alpha is stable phase. But in between you have alpha 1 plus alpha 2. So this will help you, right? So start with two ends, it will better. Start with left hand and right hand. दोनों साइड अल्फा है, तो अल्फा का फ्री एनर्जी ऑब्वियसली नीचे जाएगा, दोनों साइड से, राइट? और मैंने तुम्हें बताया कि अल्फा जब अनस्टेबल होगा उसका फेज डायग्राम कैसा है, उल्टा है, राइट? So you add them and that you add it, the diagram will be done. See, this is alpha. Alpha is stable in this side. Alpha is also stable in this side. But here this is not stable. Alpha plus alpha 2. Alpha 1 plus alpha 2. Okay? But I told this is a diagram for splitting. Alpha will split into alpha 1 plus alpha 2. This is alpha and it becomes alpha 1 plus alpha 2. So if I check the left hand, what will happen? It will be like this left hand, alpha is stable. You can see alpha is stable. This hand also alpha is stable. I can also take that. And in between alpha is not stable. So, no. Very simple. It is okay. And if this is the situation, what I can do? I can join these two.
बोले वाला बाकी 60% कितना
So this is G versus X curve for your miscibility. Then alpha becomes alpha 1 plus alpha 2. Okay, you want to find out the slope of this curve. Slope is dz by dx. Yes or no? If you want to find out the slope, that is dz by dx. Then suppose you want to find out again slope of dz by dx. It will be d square g by dx square. Second derivative. But let me tell you one important line here. At this point, slope is minus infinity. Remember, I am not going to the depth. Just remember, at this pure end, this is minus infinity. The slope is minus infinity. And at the extreme right hand, the slope is plus infinity. But how it is coming, you just think of it. I am not going to discuss that now. So you start with minus infinity slope. Now tell me, if you go down, slope is increasing or decreasing?
Increasing.
Increasing, but in the negative direction.
Negative.
Obviously, slope is increasing in the negative direction. So what I can write? Slope in negative direction. Finally, it will go and finally reach a point. This point. This point is showing 0. Now the slope is 0, right? There is no change. You cannot draw a tangent, right? Basically, for this method. So it is 0. Again, this line is moving up. So the slope is increasing or decreasing? From this point. From this is 0 slope. This is minus infinity slope. Slope is increasing in the negative direction. It reaches the point 0 point. Again, it is moving up. So it is increasing or decreasing?
Increasing.
But in positive direction.
direction.
The slope you can help. positive direction. Right? But there is a changeover. This slope, this is going up and reaching a point here. Because it is changing, you can see this one is like this, but this line is like this. Right? So this point is the maximum peak point. You can write. So this point is peak. Slope is at a peak point. Peak point. And now again, what is happening from this point? Slope is increasing or decreasing?
Decreasing.
Decreasing.
Positive
Very good.
direction.
So from this point, the slope is decreasing again.
In positive direction.
Then finally it will reach to this point. At this point, what is happening? Again, slope is 0.
0. Zero.
So here slope is again
Positive
0.
0. 0.
Okay? Then again, what is happening? It is moving down. Again, slope is increasing.
Increasing in
But in negative direction.
negative.
Right. So this line is showing you increasing. Increasing slope, negative direction. Then finally it will reach a peak point. From this point you can see again it is changing. So here slope is again decreasing.
Decreasing.
But finally here it will reach at 0 again.
0.
So this is again 0 slope. 0. Then finally from here to here, again increasing in positive direction. So slope increases in positive direction. Then finally it will reach to this point. Again this will become plus infinity. And this is plus infinity. So here we have to find out dz by dx. Right? Basically. But if you want to draw a diagram of this, the diagram will be somewhat different. What is the time frame?
5:15.
5.
Okay, fine. I will stop here. Better. We'll continue with this. Which big point? See, this curve is like this.